So part two is saying that two identical balls A and B of masses 1.5 kilograms are moving with velocities 15 meters per second and 5 meters per second respectively. It is found out that after collision, the kinetic energy lost by the balls is 37.5 joules. Is lost is 37.5 joules. So find the velocities with which the balls move after collision. So according to what Rodney had done here, he had assumed that the bodies were moving together, yet in the question it is not mentioned anywhere. It is not mentioned that maybe it is a perfectly elastic collision. I mean, yes, a perfectly inelastic collision. It is not mentioned anywhere. Otherwise, if it was mentioned like that, then you would have used this. But since it is not the case, then we simply apply the principle of conservation of momentum alone. And then we simply try to get the loss in kinetic energy as we've got in the previous question. So this is what we do here. They have said that the bodies are identical. If they are identical, it means that they have the same mass, which is 1.5. So from the conservation of momentum, we shall have that M1U1 plus M2U2 is equal to M1V1 plus M2V2. And since the mass is the same, the mass can cancel out. M1 is equal to M2, so it can cancel out. Divide by M, divide by M, divide by M, divide by M, it can cancel out. So we shall end up with our U1 plus U2 is equal to V1 plus V2. Or in case you don't want this, you can simply work it out the way it is. The way it is that our M1 is 1.5 kilograms. So 1.5 times U1 is 15 meters per second plus 1.5 times 5 meters per second. This is equal to 1.5 times V1 plus 1.5 V2. So you can see that the 1.5 is going to be cancelling out, and we shall end up with 15 plus 5, which will give us 20, being equal to V1 plus V2. So this is our first equation. That is our first equation. And then after that, since they're talking about the loss in kinetic energy, we are going to get the total kinetic energy before collision. Total kinetic energy before. And for this, we shall simply have a half times 1.5 times 15 squared, then plus a half times 1.5 times 5 squared. What answer do we get here? Then after that, you get the expression for the total kinetic energy after collision. And what do we do here? The reason we're getting the total kinetic energy before and after is because they talked about the loss. They talked about the loss. So once you subtract the two, whatever you get will be equal to 37.5 joules. So after collision, we shall have a half times 1.5 times V1, but squared for one body, then plus a half times 1.5 times V2 for the other body. And this is the same, since a half, a 1.5 is the same all through, it's same as 0.75 into V1 squared plus V2 squared. And this will give us our Roman 2. Not Roman 2, we call it equation star. What have you got here?
180 over 5.
100?
187.5.
0.5. Yes. The others, have we got the same? So the loss in kinetic energy is equal to the kinetic energy before, then minus the kinetic energy after. And what is this one equal to? It is the same as 187.5 minus 0.75 V1 squared plus V2 squared. Everything there is equal to 37.5. So meaning therefore that our V1 squared plus V2 squared will be equal to simplify that. Okay, Maha, what is that one equal to? Yes, do you get that? I'm waiting.
Yeah.
Okay. So we have two equations. And we are supposed to find the value of V1 and V2. Since we have two unknowns and two equations, then that is a simultaneous equation. That is a simultaneous equation. So you can use any method to find the value of the V1 and V2. You can use substitution, you can use any method that you feel like using. So solving these two, we can see this, that if we make V1 maybe subject of the formula from this, our V1 will be equal to 20 minus V2. So when you substitute this into this equation here, where there is V1, we shall have 20 minus V2, but squared. Then plus V2 squared equals to 200. Simplifying this will give us 400 minus 40 V2 plus V2 squared plus V2 squared equals to 200. This is squaring this. A minus B squared, remember this is the same as A squared minus 2AB, then plus B squared. That's what I've used here. A squared, that is 20 squared, minus 2 into 20 times 1, that is 20, then times 2, that is 40, V2. So this will give us, if I simplify this again, I'm beginning with V squared, I'll end up with 2V2 squared minus 40 V2. When I bring this 200 this other side, I'll end up with plus 200 equals to 0. I guess that is okay. And that is a quadratic equation in the form ax squared plus bx plus c equals to 0. So from the calculator, what is V2 equal to? What is V2 equal to?
I don't know if I used the correct method in the calculator. Is it negative 10?
Negative 10. No. What have the others got? 10 and 2. Have you got 10 and 2?
Yeah. I
But you
got
got
negative 10 and 2.
and negative 2. So where is the problem? The B is a minus 40. A is 2,
Oh,
B is
okay,
minus
okay.
40, and then the C is 200. You get positive 10, positive 2. So if V,
Okay, yeah, yeah,
so
yeah.
if V2 is positive,
I've got those.
okay, so if V2 is positive 10, when you substitute this one here, it will give us the answer as 10. Okay? Then if V2 is 2, then V1 will be equal to 18. So that is how you can state your answers. Either you take this or you take this. So that is what you are supposed to do. That is what you're supposed to do. Okay, let me give you some time to have this down. I'm recording this video. I'm going to post it maybe on YouTube. Maybe if you give me authorization, I'll be putting it there. Okay. So I was saying that don't assume, the question was not saying that the bodies moved together. So I'm saying here that do not assume anything. Maybe what kind of collision is this? Remember, we have three types. We have elastic, we have inelastic, and the perfectly inelastic. Three of them, elastic, inelastic, and perfectly inelastic. What kind of collision is this?
Um,
Okay. Okay,
in
it is what?
inelastic.
It is inelastic, correct. It is inelastic. If it was perfectly elastic, or what we call elastic, then the kinetic energy will be conserved. But in this case, it is not conserved. And if it was perfectly inelastic, then this one would be the answer. Because the common velocity, they'll be moving together with the common velocity. That is what perfectly inelastic means. They two move together as a single body. And that is what, Andre, you had assumed this. In case you remember your answers. Okay? In case you remember your answers here, you had got this 10.
Yeah.
Yes. But it is not the case. So it can either be inelastic or perfectly inelastic, depending on the answers that you've got here. They can even ask you that, which velocity is V1 and V2 give you a perfectly inelastic collision? It is 10 meters per second. And then for inelastic, it will be 2 and 18. Okay, yes, are we done? Define specific heat capacity of a substance. What did you say, Martina, here?
Specific heat capacity is the amount of heat required to raise the temperature of 1 kilogram mass of a substance by 1 Kelvin.
By 1 Kelvin. Very good. So 1 kilogram, specific 1 kilogram mass of the body, that is correct. Then Roman 2, explain why the specific capacity of a body in solid state is lower than its specific capacity in liquid state. What did you say here? Anyone?
Um, the molecules of a body in solid state are more tightly packed than when it's in liquid state. Hence, is a lower surface area needed to cover for heat transfer. That's the lower specific heat capacity.
Hence the low specific heat capacity. Okay. Would I be able to give you the 3 marks here?
I'm not sure. Could we?
in solids, we are saying that solids, we have the molecules are closely packed together, and then in liquids, we have the molecules are somehow spaced. So meaning that in case you are to supply the heat, because of this distance between the molecules in liquid state, the heat takes a longer time to reach the other molecule, and therefore, the specific capacity of solids is bigger than the specific capacity of liquids. Okay, that is one. That is one reason. Any other reason that you can think? So if the increase in volume, it means that the molecules will simply be getting further and further apart. So meaning that the heat will have to travel through a longer distance to reach the other molecule. So which means therefore that we have to apply more heat in order to overcome the atmospheric pressure exerting on the liquids. And that's why the specific capacity of solid is always lower and liquid is always higher. So you can give those two reasons there. The first one about the arrangement of the molecules, and then two, in overcoming the atmospheric pressure. That could be the other reason there. Then part B was saying that with the aid of a label diagram, describe the method of mixtures to determine the specific heat capacity of a solid. Now, this question here can be answered in two ways. Number one, if they mention about a solid, here you have a choice, okay? You can either use the electrical method or you can use the method of mixtures. Electrical method or the method of mixtures. And the electrical method basically works for metals or good conductors of heat, and the method of mixtures works for this for the insulators or poor conductors of heat. Poor conductors of heat. For example, rubber. Now, if we've been given a question like this, it is always better that you use the electrical method. Why? Because it is the most accurate. It is the most accurate. That is the reason. And in case the question is particularly saying that describe an experiment to determine the specific capacity of a good conductor of heat of a metal, just know that we're going to be talking about the electrical method. Likewise, the question says that describe an experiment to determine the specific capacity, describe the accurate method of determining the specific capacity of a solid. If they mention the word accurate, then still that is the electrical method. Still that is the electrical method. And if they are specific and say that describe the method, describe an method of mixtures, actually this question, yes, it is even about the method of mixtures. So if the method of mixtures, then it means that you're going to describe for poor conductors of heat. The poor conductors of heat. So what do we do here? What do we do here? Of course, you need to remember that in order for us to describe this method, in order to describe any method accurately, you must be recalling the final expression. You must be recalling the final expression. So if you know that you're going to be dealing with the method of mixtures, what do you need to recall? You need to recall that heat supplied is equal to heat gained. And the assumption is that there are no heat losses to the environment in this case. Now, what is supplying the heat? It is the hot body. And what is gaining the heat? Maybe it is the water and the calorimeter. So in other words, what are the equations here? We'll be having mass of the body, specific capacity of the body, times temperature theta 3 minus theta 2 being equal to mass of water, specific capacity of water, plus mass of the calorimeter, specific capacity of the calorimeter, then times theta 2 minus theta 1. This is theta 1. Why am I having it like this? It is simply coming from this, that first you have a container where you're going to boil the water, and then you have your solid. This is the solid, that is the poor conductor of heat. You heat it up to a given temperature, which I'm calling theta 3. It can be the boiling point of this water, maybe 100 degrees Celsius. Then you have the heat shield here. Then you have another calorimeter of known heat capacity and having its own mass of water at the initial temperature theta 1. Okay? So once you remove this body from here and quickly transfer it to this, it will be our hot body, and its heat absorbed will be equal to mass of the body, specific capacity of the body times temperature theta 3 minus the final temperature of the mixture, which is theta 2. And this is got by mass of water, specific capacity of water. The combination of this one is the heat capacity of the water, times theta 2 minus theta 1, then plus mass of the calorimeter, specific capacity of the calorimeter, into theta 2 minus theta 1. Now, since this one is the same, that's why I'm putting it outside here. So from this, our conclusion will be that the specific capacity of the solid will be equal to mass of water, specific capacity of water, plus mass of the calorimeter, specific capacity of the calorimeter, then times theta 2 minus theta 1, then everything divided by mass of the body times the temperature theta 3 minus theta 2. Now, this is what I am calling the conclusion. If you know the conclusion, then you can think of what to write in whatever way. What do you need to remember here? In your description, you're going to be talking about the mass of water in the calorimeter. You're going to talk about the specific capacity of the calorimeter, mass of water, which is MW, and then the specific capacity of water, mass of the calorimeter, specific capacity of the calorimeter, temperature, the initial temperature of the water in the calorimeter. This is the final temperature of the mixture, final temperature of the solid alone, and then mass of the body. So you need to talk about each of these ones here. And once you talk about each one of these ones here, then you are assured of a mark. You're assured of the mark from each of those. But remember that you need the diagram, you need the procedures, you need the observations. Now, the observations that I'm talking about here is that there can be values, can simply be things you're supposed to do. For example, here there can be the measurements. Those are observations. Measure and record the mass of this, measure and record the temperature of this. Those are the observations. And then finally, the conclusion. So this is what you were supposed to do. That heat a solid in water, in boiling water, up to a temperature theta 3. Then remove it and transfer it quickly, shaking off the water, transfer it quickly into another water whose original temperature was already measured. You can just phrase it in any way that you want. Into water in another calorimeter of known heat capacity, MCCC, and of known initial temperature theta 1. Then continuously stir up to a final temperature theta 2 of the mixture. The highest observed temperature of this one here, of the mixture, which is theta 2. Then afterwards, you simply come and substitute in this equation here. You'll have got all the marks there. I've not written everything here, but that is what we do. You draw the diagram, tell us the procedures, the observations, especially the observations, and then the conclusion. This is the conclusion. So I hope you have that. You can refer to your notes and check what you have there. Then the question that gave us challenge here was the calculation. Advantages of the continuous flow method over the method of mixtures. What did you write here?
Continuous flow method can be used to measure a specific heat capacity of gases.
That is one, correct?
While there is no need for cooling correction when using continuous flow method.
Okay, very good.
Yeah, those are the 2 I wrote.
And cooling correction can simply state it as saying that there's no need of, in other words, the heat losses the environment are catered for. The heat losses the environment are catered for, unlike for the other method of mixtures. Okay, let's go to the calculation. I have a little time remaining. So in a continuous flow current experiment, water flows at a rate of 5 grams per second, and a liquid X flows at 8 grams per second to maintain the same temperature difference. And the power supply, as in the case of water, find the specific heat capacity of liquid X. What were you supposed to do here? Now, for the continuous flow method, you remember that we have 2 equations, IV T. Let me just start from first principles and I show you how it comes out to bring my friend Ortega. So heat lost. Okay, I didn't want to do it because of time. We have the constant flow head tank here. We have the tap of water, and then this is down. Let me do it like this. So this is our tap bringing the water. Then this is okay. This is our diagram. Okay, let me do it the other side. Let me do it this other side like this. Okay. So we have this container here. Then we have our vacuum. This is like a vacuum. I'm just doing a simple sketch of this apparatus here. Then we have the outflow and then the thermometer like this. And then we have another thermometer. This is thermometer theta 1. This is thermometer theta 2. And then this is an insulator. This is thermometer 2. And then this other side, we have a coil, a heating coil. And then we have the source of current. We have the switch. We have the the ammeter. We have the voltmeter. Yeah, like that. So this is our vacuum. Now in this diagram here, when you're doing this diagram here, no matter how you draw it, it is very important that you take note of this, that this tube here is the overflow tube. That in case the water rises above this way, the excess water will simply flow out like this. And then make sure the diagram is filled with water like I'm doing here. Otherwise, in case you draw an empty container, then you'll lose the marks. You lose the marks like this. And then number 2, make sure that the voltmeter is connected across. In other words, it's connected in parallel with the heater. This is the heater, the heating coil. This is the heater or the heating coil. So the voltmeter is always connected in parallel, and then the ammeter is always connected in a series. Otherwise, in case you interchange them, then you'll be gone. Now, in this case here, what is supplying the heat? It is the heater. So heat supplied IVT is equal to the amount of heat absorbed by the water, which is, you can call it MC, change in temperature, and then plus the heat loss to the environment. We use capital H. Now, to talk about the rate of heat transfer, I'll simply have to divide everything by T. So I'll have the power supplied is equal to MC, change in temperature, then plus the H, where this H here is the same as the capital H divided by this time T. So the capital H is the heat lost, and then the small h is the rate. Now, this experiment is carried out 2 times. So shall be having I1, V1, M1, C1. Since we have, now here we're comparing 2 liquids. We're comparing water and the liquid X. So I can call this on our C1. Otherwise, if it is just the same liquid like in the experiment, then you will simply be using having CCC. Okay? Then for liquid X, I'll be having I2, V2 is equal to M2, C2, change in temperature, then plus the H. And this is equation 1, this is equation 2. When you subtract these 2 here, you'll end up with I1, V1 minus I2, V2 is equal to M1, C1, change in temperature, minus M2, C2, change in temperature. And then the H cancels out. Now, coming back to our question here, we're having 2 minutes, saying that in a continuous flow calorimeter experiment, the water flows at a rate. This M here, I've divided, maybe I make it capital, okay, let me just divide this one by T. Let me just divide this one by T. We're just writing the M to mean M out of T. Let me call it M out of T, like that. So the flow rate, the water flows at this rate and the liquid X flows out at this rate to maintain the same temperature difference. So this temperature difference is the same for both of them. It is the same for both of them. To maintain the same temperature difference and the power supply as in the case of water. So if this one is the same as this, then it means that M1 out of TC1 change in temperature is the same as M2 C2 change in temperature then out of the time T. In other words, equation 1 is equal to equation 2. That's what I'm trying to bring. So the H cancels out. That is if they maintain the same power supply. Now, substituting our values here, the mass of flow of water is 5 grams per second, 5 grams out of 1 second. Times the specific capacity of water, which is 4200, times the temperature change. This one here cancels out as well. Same temperature difference. 1 minute, 1 minute. So this one cancels. So this is the same as 8 grams out of 1 second, then times the specific capacity of liquid X. So using this idea, you can then catch it for your specific capacity of liquid X in joules per kilogram per Kelvin. Now, I can also comment about this, that in case you want, you can change this unit to kilograms. But since it is grams, they can cancel out. That's why I left it there. But in case you want, you can change it to kilograms and kilograms as well. So with this, I'm stopping here for now. You can complete this. I can say that have a great night. See you tomorrow in Waves.